Welcome to my new calculus channel. My name is John Gabriel. In this video, I'm going to talk to you about two very important concepts, namely continuity and smoothness. But before I do that, it's imperative to talk a little bit about what it means to be a path or a line or a point. Now, most of you probably do not recall what is written in the elements and the exact definition of these concepts, but they were very well defined by the ancient Greeks. A point is really the idea or concept of a location or a position or a place. In fact, the very word for point in Greek means place. So, or flag, place or flag. In fact, the derivative for all the words that signify point actually go back to the same original root word, which is flag. Simea is flag, simeo is point. And these geometric objects are not tangible. You can't reify them in any way except through the concept of distance and the properties which certain curves have. For example, it makes absolutely zero sense to talk about lines on a point. A line does not consist of points. Yes, is that shocking to you? Well, it's true. There are flags or locations along a path or a line which we use to denote the positions. They're not part of the line any more than a flag is part of the line. Let's look at some examples. So, if we begin with any path, like you see this blue path here, the flag is really just the position along the path. It's not part of the path any more than this flag here or road sign is part of the road. Now, a road actually has breadth and length, but a line doesn't have any breadth. It doesn't contain anything. It's just distance. In fact, the most important attribute of this blue line that you see here is its distance. And what I've drawn here, as you see on the screen, is not a line. It's not even a curve. It's a visualization of a distance. Think about that for a while. A straight line is a visualization of the shortest distance between 2 points. That's all it is. You can't construct it. It's a distance. Distance is length. The same with any other geometric object, a triangle, a circle, or anything else. So for example, if you look at other things, other geometric objects such as an ellipse, you'll notice that they have certain properties, and they're all in terms of distances. So for example, the distance of BF to FI is always constant. BF is the distance from the directrix to a point, and FI the distance from the point on the ellipse to the focus. So this distance here is always the same, okay? And that's one of the important properties of a directrix. So let's get rid of that. And the same thing happens with a parabola, okay? Its eccentricity is 1 because these two distances have the same ratio, right? So, for example, you can move this position anywhere you like along the parabola, and this ratio here remains constant. And the same thing happens with the hyperbola, which is this particular geometric object here. You can't visualize it. These lines here are not the hyperbola. They're just visualizations. We care about this distance and the property that it has in relation to the foci. Okay, so we cannot talk about points being part of a line. And just for a last example here, in the circle we have the same story, okay? So again, all the lines on the circumference of the circle have the same distance to the center. All the positions on the circle have the same distance to the center, and that's just the special property of the circle. So those are all the geometric objects. Now, if we move this, supposedly if we move along the path, we're not moving a point. Points don't move, they're stationary, okay? This is just a visualization of what happens as we traverse this path. So the orangutans in mainstream academia like to think of things like piecewise functions. So imagine now that you have a piecewise function. I don't know if it's occurred to you yet, but all these lines that I've been drawing here don't actually exist. They're visualizations. The paths exist. But can you have a path like this where you don't have flags for this region here? Well, you can have innumerably many paths that join the endpoints of these two lines, okay? So innumerably many paths. You can't suddenly say, oh, they don't exist because this function here, which is defined by a specific rule, suddenly doesn't have flags at these positions here. That's just absolute rot and ridiculous. Okay, so there is no such thing as a piecewise function. In fact, by definition, a function has one rule, not more than one rule. And so continuity really is the fact that there exists a flag for every part of the path. Okay, you can't remove those flags. They're always there. But the idiots in mainstream academics do stupid things like removing those flags. So that makes absolutely zero sense. The next thing I'd like to talk about is smoothness. So what makes a path smooth, by the way? What makes a path smooth? You're looking at it. You see that green line there? If you can construct only one green line at every point along the path, then that path is smooth. And let's see an example of where it's not smooth over here. See, you can construct infinitely many tangents at any one of these sharp points here. So along this short distance or this interval here, it's not smooth if we have to choose this particular path to join these two curves. Okay, so, and in reality, the original one is still there. It's just that we are not visualizing it anymore, but it's there. And all the innumerably many other paths that join these two curves are still there. So it makes absolutely zero sense to talk about piecewise. And you cannot even talk about limits if continuity and smoothness are not already in place. Do you understand that? So, for example, you can't suddenly just remove the flag at one position and say that the function is no longer continuous there. All right, unless the rule does not define the function there. So, for example, if you have a hyperbola, there is no flag at the point 0, 0, or a flag that will line up with that particular location vertically, so to speak. And in that case, we say the curve is not continuous, but it's not piecewise because all the points are there, and you can't really remove the points that are already there because that makes no sense. If the points aren't there, then it's discontinuous if they're not defined. So if there's no flag at a particular part of the path, then it's not continuous there. So to be smooth, only one finite tangent line can be constructed anywhere along the path, okay? That means it will be smooth. And that covers what I'd like to say about continuity and smoothness. To use any of the first order logic definitions that you find in real analysis, which talk about limits at a point and continuity at a point, you need to have those particular properties in place already. In other words, the curve must be both continuous and smooth. And trying to redefine it in terms of those first order logic statements, the epsilonics, is very circular, because, for example, if I wanted to know the limit at this particular point here, I must assume that the path here has flags everywhere, okay? Because if it doesn't, then I have a problem. Well, I hope you've learned something about continuity and smoothness in this particular video, and trust you will join me again next time. I'm John Gabriel, and this is New Calculus Channel. Goodbye.